Okay, and we come to our last video on the matrix series. In this video, we're not going to be doing any new content. I've just got two matrix questions which we're going to have a look at. So let's delve into the first one of these. First question. A 2x2 matrix M has the following properties. 3, 1 is an eigenvector, and we've got its eigenvalue. The acute angle between the eigenvectors is pi on 4, and the other eigenvalue is 5. And we are going to use this information to determine two possible matrices that satisfy these conditions for n. Okay, so the first thing to pick up on, I think, is the fact that the two eigenvectors have an angle of pi on 4 between them. So that tells us that if we dot product these vectors together, so 3, 1 dotted with the other eigenvector, which we do not know what it is, so let's call it v1, v2, then that is going to equal the modulus of 3, 1 times the modulus of v1, v2 times the cosine of pi on 4, or it could be 3 pi on 4. So let's make a little note that it could be 3 pi on 4 here. But it will turn out that actually we don't need to worry too much about that because we're about to square it anyway, so that'll disappear. But it is just worth bearing in mind that there could be 3 pi on 4 between the eigenvectors as well. Okay, right, so let's evaluate this equation. So this dot product on the left is going to be 3v1 plus v2. And then we've got this modulus, which is going to be root 10. And then we've got this modulus here, which is going to be the square root of v1 squared plus v2 squared. And then we've got this cosine function here, which is going to be root 2 on 2. Okay, so that gives us an equation which relates v1 and v2. So that's v2 squared there. Okay, so let's get rid of these surds. So I'm going to times the whole thing by 2, and then I'm going to square the whole thing. So I'm going to end up with 6v1 plus 2v2 squared on my left-hand side. And that's going to equal root 10 times root 2 squared is 20. And then I've got v1 squared plus v2 squared. All right, this is going to be a quadratic equation in the v's. So we're going to get 36 v1 squared plus 24 v1 v2 plus 4 v2 squared, and that's going to equal 20 v1 squared plus 20 v2 squared. Subtracting that across the other side, I'm going to get 16 v1 squared plus 24 v1 v2 minus 16 v2 squared will equal 0, and then I can divide the whole thing by 8 actually. So 2 v1 squared plus 3 v1 v2 minus 2 v2 squared equals 0. Okay, right, so this has to be true for the two eigenvectors to have a pi on 4 angle between them. And if I did have 3 pi on 4, then that would have been negative root 2 on 2. And when I squared it, then it would have disappeared anyway. So as I said earlier, that's already taken care of. Okay, so we've got this equation here. This is a quadratic. I'm going to say v1, therefore, is minus b. So it's going to be minus 3v2. So I'm pretending it's a quadratic in v1 only. So v2 then becomes a kind of constant. And this will allow me to express v1 in terms of v2. Then I've got plus or minus b squared. So that's going to be 9v2 squared. Minus 4ac. So that's minus 4 times a, which is 2, times c, which is minus 2v2 squared. That's all square rooted. And that's all divided by 2a, which is 4. Both of these terms have a v2 squared, so I can pull that out of the square root, and then actually I can completely pull that out of the numerator, and I'm going to be left with minus 3 plus or minus 5 over 4 times v2. So I've got v1 in terms of v2. Okay, right. So from there, I can say V1 is either a half V2 or V1 equals -2 V2, depending if I take the plus or minus. So I just need to choose a vector which satisfies these. So we want V1 to be half of V2. So let's choose V1 to be 1, and that means V2 would be 2. So that vector satisfies that. And over here, we want V1 to be the negative twice V2. So if I call that a -1, say, then that would be a 2. So those are my two possible eigenvectors for V. Okay. So I've got my two eigenvectors. That'll give me two possible matrices for M. Go back to the criteria. The other eigenvalue is 5, and then I've got this eigenvector which I worked with to get V in the first place. So I've got the two eigenvectors and their corresponding eigenvalues, so therefore I can calculate the matrix. So considering just this one, I can say that M could be, let's call it M1, could be the eigenvector matrix 3, 1, 1, 2 times the eigenvalue matrix, which was 10, 0, 0, 5, multiplied by the inverse of this, which is 3, 1, 1, 2 inversed. Okay, so that's using some of the theory which we looked at in the previous video. The eigenvector matrix multiplied by the eigenvalue matrix multiplied by the inverse of the eigenvector matrix, and that equals the matrix itself. Okay, so that's using this eigenvector. And the other eigenvector, this will give me a different M matrix. So 3, 1 was still the other eigenvector, but this time it's 2 minus 1 times by 10, 0, 0, 5 times by 3, 1, 2 minus 1 inversed. Okay, so we're going to carry out these matrix products. So we're going to get 30, 5, 10, 10. Multiplied by the inverse of this, that's 6 minus 1, so that's times a fifth. And then we're going to swap the lead diagonals and change the sign of the non-lead. So that becomes a 2 and a 3. And then those two will change to minus 1s. The fifth can come into this matrix quite nicely. So it's going to be 6, 1, 2, 2. Multiplied by 2, minus 1, 3. And that will give me my first possible matrix for M. So 12 minus 1 is 11. Minus 6 plus 3 is minus 3. 4 minus 2 is 2. And minus 2 plus 6 is 4. Okay, so that's the first one of the matrices. This matrix satisfies all three of the criteria from the question. And this one does as well. So let's carry out this product. So we're going to have 30, 10, 10, minus 5. And then we're going to times it by the inverse of this matrix. So that's got a determinant of minus a fifth. So minus 6. Oh, sorry. Minus 3, minus 2, yeah, minus a fifth. And then we're going to swap the lead diagonal, so minus 1 and 3. Change the sign of the non-lead, so that's minus 2 and minus 1. Again, the fifth can go into this matrix quite nicely. So we're going to be left with minus 6, minus 2, minus 2, positive 1. And then carry out this product. And we get 6 plus 2 is 8. 12 minus 6 is 6. 2 minus 1 is 1. And 4 plus 3 is 7. And those are the two matrices for M. Okay, so that's the first question. So those two matrices satisfy all of those criteria. Okay. All right, the second question. Okay, so we have this matrix here. Okay, 3 by 3. We've got two unknowns in the matrix. Okay, we've got a mu plus 2 here, and then we've got a lambda down here in the bottom right. It's got three distinct real eigenvalues, lambda, mu, and nu, such that lambda, mu, and nu are all integers. Okay, so the mu there, that is one of the eigenvalues of the matrix, as is lambda down there. Okay. So part I, we're going to use det m minus lambda I is equal to 0 to deduce that mu equals 11 minus 2 lambda. Okay, so part I, let's do that down here. We'll come back to the rest of the question in a bit. So part I, we're going to, you know what, actually, it might be a better idea if I do this. Okay, do part I here. All right, so deduce that this is true. All right, det m minus lambda I. So we're going to take this matrix, we're going to subtract lambda off the lead diagonals, and then we're going to set that determinant to be 0. So we're going to have 4 minus lambda, 0, 1, mu plus 2, minus 1 minus lambda, 3, minus 3, 3, and then lambda minus lambda, which is 0. And we're going to find the determinant of this matrix, and we're going to set that to be equal to 0. And that will give us a relationship between lambda and mu, which will hopefully simplify to what the question tells us it does. Okay. All right. So, determinant of this matrix, we can see we've got 2 offset zeros, which is nice because it means out of the 6 calculations, 4 of them will be 0. So that's going to be 0, that's going to be 0, and that's the only one in the positive direction. So we're going to have 1 times mu plus 2 times 3. And then in the negative direction, we've got, I told a lie, sorry, that one's not 0. The 2 zeros line up there. So there's going to be 3. Apologies. Right, let's do the non-lead diagonal. So we're going to do minus that times that times that. So it's 1 times minus 1 minus lambda times minus 3. And then we've also got that times those two. So it's minus 4 minus lambda times 9. And that equals 0. Okay, I'm going to tidy this up. So I've got 3 mu plus 6. Lots of negatives going on here, so be really careful with sign errors for questions like this. Minus 1 times minus 1 times minus 3 is a total of negative 3. Minus 1 times minus lambda times minus 3 is a total of minus 3 lambda. Minus 36. And then minus minus, so it's plus 9 lambda is equal to 0. And just be careful because the answer's in the question, so you don't fudge the answer, just take your time with it. We're going to have 3 mu is going to be equal to, let's push everything across the other side. So we're going to have minus 6 lambda. 36 plus 3 is 39, minus 6 is 33. And then divide it by 3. And we're going to end up with mu is equal to minus 2 lambda plus 11, which equals 11 minus 2 lambda. That's required. Okay, so there we go. We have shown that mu equals 11 minus 2 lambda. All right, part 2 of the question. We're going to use the determinant of m minus mu I is equal to 0, and the result in part I to deduce that this cubic is true, and we're going to find integers for a and b. Okay, so essentially this is going to give us another relationship between lambda and mu. Looks like it's going to be a cubic this time. And then we're going to sub this in to get rid of our mu's, so we're left with a cubic in lambda only. Okay, so that's our mission. So go back to the matrix. We want to do the det of this minus mu. Det of 4 minus mu, 0, 1, mu plus 2, minus 1 minus mu, 3, minus 3, 3, and lambda minus mu is equal to 0. Okay. All right. So calculating this determinant, we're going to do the lead diagonal. So we've got 4 minus mu times minus 1 minus mu times lambda minus mu. Then we've got that times that, which is 0, and that times that, which is going to be plus 3 into mu plus 2. So those are all the positive directions. Negative direction, let's do this times those two. So that's going to be minus 9 times 4 minus mu. That negative direction is 0, and then we've got this negative direction here, which is the one with all the negatives. So I've got minus 1 times minus 1 minus mu times minus 3. And this whole equation, expression, will equal 0. Okay, right, so where's my lambda? That disappeared. Ah, there it is. Okay, right, so what I'm going to do is I'm going to use the result from part I here to replace the mu's in this equation here, and that will leave me with an equation with just lambda. So mu is that, so we're going to end up with 4 minus mu, so that's going to be 2 lambda, and then we've got 4 minus 11, so it's minus 7. And then I've got minus 1 minus mu. So minus 1 minus mu. Again, we're going to have the 2 lambda because we're minusing mu. And then it's minus 1 minus 7, so it's minus 12. And then we've got lambda minus mu. So that's going to give us 3 lambdas. Lambda minus minus 2 lambda. And then I've got minus 11. Okay. And then I've got plus 3 times mu plus 2. So that's going to be 13 minus 2 lambda. And I've got minus 9 into 4 minus mu. So that's going to be 2 lambda. And we've got 4 minus 11, which is minus 7. And then I've got this one here, which is going to be plus 3. So minus 1 times minus 3 is plus 3. Minus 1 minus mu is 2 lambda minus 12. Okay. That equals 0. All right, so that's now replaced all of my mu's, and that's going to leave me with a cubic in lambda, which once I play around with that, I should end up with this. I can use the coefficients of lambda cubed and lambda squared to help confirm my answer, and then I can see the values for A and B. Okay, so let's tidy this up. It's quite a mess at the moment. So the cubic term and the quadratic term are only going to come from here. The cubic term, we've got 2 times 2 times 3. So that's 12 lambda cubed. The quadratic term, sorry, I'm just going to get my calculator in. Okay, quadratic term. We're going to have 2 times minus 11. So 2 times 2 times negative 11. We could have 2 times 3 times negative 12. So plus 2 times 3 times negative 12. And then we could have 2 times 3 times negative 7. So that's plus 2 times 3 times negative 7. And that gives us minus 158. So minus 158 lambdas. Okay, sorry, lambda squared. Now the lambda term, we could have the 2 times minus 12 times minus 11. Okay, 2 times minus 12 minus 11. We could have the 2 times minus 7 times minus 11. And we could have the 3 times minus 7 times minus 12. 670. And then the constant term, we've got 7 times 12 times 11, which is 924 negative. Okay, so that has expanded this bracket. Then we've got plus 39, minus 6 lambda, minus 18 lambda, plus 63 lambda, plus 63, plus 6 lambda, minus 36 is equal to 0. Okay, and tidy that up. Got 12 lambda cubed minus 158 lambda squared. The lambda terms are in quite a few places. So we've got 670 here. We then got minus 6 there. We've then got minus 18 there. And then plus 6 there. That's 652. And then the constant term, minus 924 here, plus 39, plus 63, minus 36, minus 858. Okay, right. And then look at the question. We notice that the coefficient is 6, and we've got a coefficient of 12. We also notice that all of these are even. So we can divide the whole thing by 2. So we get 6 lambda cubed minus 79 lambda squared. That's good. That's reassuring because that's what it was in the question. Half of that is 326. And then half of that is 429. Okay, so A was 326 and B was minus 49. Excellent. All right, that's it. So it says A and B are integers to be determined. Because we've written it in this form, that has implicitly stated what our A's and B's are, but you could state them explicitly if you wanted, but you wouldn't have to. So A equals 326 and B equals minus 429. Okay, excellent. Part 3. Hence find the 3 eigenvalues of M. All right, so we've got a cubic equation here, which one of the eigenvalues will satisfy. So we can jump into our equation solver mode in the calculator. And it's a cubic equation, so a polynomial of degree 3. And it's got coefficients of 6, minus 79, 326, and minus 429. And that gives us these 3 possibilities for lambda. So part 3, lambda could equal 6.5, 3.6 recurring, or 3. Okay, so 6.5, that's 13 halves. 3.6 recurring is 11 thirds. And the other one was 3. Okay, so those are the 3 possibilities for lambda. It's one of those. But if we look back at the question, we are told that lambda, mu, and nu are all integers. So that means lambda can't be 3 halves or 11 thirds. So therefore lambda is 3. Just conclude, but lambda is an integer. Therefore lambda equals 3. Okay. All right, now we've got lambda is 3. We can go back to this statement from part I to state that mu must be 11 minus 6, which is 5. So mu equals 11 minus 2 lambda, which equals 11 minus 6, which is 5. So mu is 5, lambda is 3. And then the third eigenvalue was denoted with the letter nu, and we're going to use the trace of the matrix for that. So we know, again, based on a previous video that I've done, lambda plus mu plus nu equals the trace of the matrix. Now the trace of the matrix is the sum of the lead diagonal. So it's going to be 4 minus 1 plus lambda. Okay, so I've got this equation. The lambdas will cancel. So mu plus nu equals 3. But I know that mu is 5, therefore nu is negative 2. Okay, those are my 3 eigenvalues. Excellent. All right, part 4. Find the corresponding eigenvectors. Okay, well, at this point, this now just becomes your standard, here's a matrix, find the eigenvectors, because I've got the matrix and I've got my eigenvalues. So, part 3, I'm going to go through each of these eigenvalues in turn. So let's set lambdas to be 3, first of all. And that's going to give us 1, 0, 1. Mu plus 2 is 7. Minus 1 minus 3 is minus 4. 3 minus 3, 3, and 3. Okay, so just to clarify exactly what I've done there is I have plugged in into this matrix here. Lambda is 3 and mu is 5. And then I've subtracted lambda off the lead diagonal. Oh, so that should be 0, shouldn't it? Okay. All right, so that vector multiplied by the eigenvector v1, v2, v3, that is going to equal the 0 vector. 0, 0, 0. Okay. Now to find v1, v2, v3, we can punch this through our calculator. There'll be infinite solutions. So simultaneous equations with 3 unknowns. And we're going to have 1, 0, 1 in the top row, 7, minus 4, 3 in the middle row, and minus 3, 3, 0 on the bottom row. Infinite solutions, which is good, we expected that. So you can choose a value for z, and then that locks in the other two. So I'm going to choose z to be minus 1, and the other two will be 1. And then I repeat that process for the other two eigenvalues. So mu is 5. So that's subtracting an extra 2 off this lead diagonal. So it'll be minus 1, 0, 1, 7, minus 6, 3, minus 3, 3, minus 2 times this eigenvector will equal the 0 vector. So to calculate the corresponding eigenvector for mu is 5. All I need to do is go back to this matrix and change these numbers on the lead diagonal. So that's going to be a minus 1, that's going to be a minus 6, and that's going to be a minus 2. Again, infinitely many solutions is what I'm expecting. I'm free to choose z. I'm going to choose z is 3 so that everything is an integer. So z is 3, y then will be 5, and x will be 3. So 3, 5, 3. And then finally, the third eigenvalue, nu, which was negative 2. So to get from 5 to negative 2, I'm going to subtract 7. So that's adding 7 to the lead diagonal. So we're going to get 6, 0, 1, 7, 0, 3, minus 3, 3, 4. No, we're going to add 7, sorry. That's a 1, and that's a 5. Okay, times that by v1, v2, v3. And that's going to equal the 0 vector. And that allows us to find a vector here. So again, just changing the lead diagonal on this matrix. So 6, 1, and 5. Infinitely many solutions again. Free to choose z. I'm going to choose z to be minus 6. And then my y would be positive 11. And my x would be positive 1. Okay, so those are my 3 eigenvectors. Okay, where do we get to? 2 more parts. Find matrices P and Q such that Q is a diagonal matrix and M to the power 5 is PQ inverse P. So this is using that eigenvector eigenvalue matrix theory, which we actually used in the previous question. So for part 4. We've got our 3, sorry, part 5. We've got our 3 eigenvectors. So P then is just the eigenvector matrix. Doesn't matter which order you put them in. So 1, 1, minus 1, 3, 5, 3, 1, 11, negative 6. There would be 6 possible answers for P. Okay, it doesn't matter which order you put those in. And then Q is going to equal the matrix of eigenvalues, but then it must be in the same order as we had here. So we got 3, 0, 0, 0, 5, 0, 0, 0, minus 2. But just be careful because in the question, it wasn't m is equal to that. It's m to the 5 is equal to that. So Q therefore is going to be that matrix to the power 5. P is still P. Excellent, so we just need to evaluate that matrix. So Q then is 3 to the power 5. (243), 0, 0, 0, 5 to the power 5. So it's 3,125, 0, 0, 0. And then minus 2 to the power 5 is negative 32. Okay, so there's matrices P and Q, and that's all it asked for. Okay, find matrices P and Q. All right, and then one final part of the question, use the Cayley-Hamilton theorem to express m to the 4 in terms of m squared, m and I. Okay, so the Cayley-Hamilton theorem says that a matrix satisfies its own characteristic equation, and the characteristic equation is the polynomial equation which has the eigenvalues as roots. So the characteristic equation is going to be lambda minus 3 times lambda minus 5 times lambda plus 2 is equal to 0. I don't need to find det m minus lambda because I know the 3 eigenvalues, so I can just jump straight to the characteristic equation. So that's lambda cubed, minus 3, minus 5 is minus 8, plus 2 is minus 6 lambda squared. And I've got 15, minus 10, minus 6 is minus lambda. And then I've got minus 3 times minus 5 times 2 is plus 30. So the Cayley-Hamilton theorem says that m cubed minus 6m squared minus m plus 30i is equal to the 0 matrix. Okay, and we want m to the 4. So if I take that equation and times it by m, so m to the power 4 minus 6m cubed minus m squared plus 30m is also the 0 matrix. So therefore m to the 4 is going to be 6m cubed plus m squared plus minus 30m. But it wants m to the 4 in terms of m squared, m and I. At the moment, I've got m to the 4 in terms of m cubed, m squared and m. So I'm going to use this again to get rid of the m cubed. So it's going to be m to the 4 is going to be 6 times m cubed, which is 6m squared plus m minus 30i, plus m squared minus 30m, and then tidy that up. So I'm going to get 37m squared plus 6m minus 30m is minus 24m, and then minus 180 times I. That's it. Okay, there we go. Right, that finishes matrices. In our next subtopic, we're going to be looking at recurrence relations and how to solve those. Yeah, if you have any questions, as always, just drop them in the comments below, and thanks very much for watching. I hope you found this series useful.